So chapter, or I guess 7C, starts us off with undoing these derivatives. So that's what antiderivatives are. So we're looking at undoing our derivatives along the way. So an antiderivative is just the inverse process of finding the derivative. So the notation of it is capital F prime of x equals little f of x. So what that means is we have this function, capital F of x, and when I take the derivative of it, that's why it's f prime of x, we get little f of x. Okay. So those are kind of the different ways that we can see it. So we're going to find capital F of x by working backwards. So this is what we're used to seeing, f of x. So this is what our normal function is. So we're pretending like, hey, that's the derivative. Let's go backwards now. So what I'm going to have you guys do is I'm going to have you work backwards from this function, f of x equals 4x minus 1. And I want you to think about if you undid this. So if this was the derivative, think back, try to work backwards and think, what must the original function have been? So when we work backwards and we try to find our derivative, you end up getting capital F of x, because again, we're going backwards. So don't put f of x, do capital F of x. What did you guys get for a function? 2x squared what? Minus x. So if I take the derivative of this, do I get 4x minus 1? Okay, good. So that is an absolute possible situation. Good. Now, would you all please take a moment and go ahead and take the derivative of each of these? Again, that's what d dx means, is you're taking the derivative of each of these functions. So take a moment, please. Okay, so when you take the derivative of the original one, we kind of did this already. You get 4x minus 1. When you take the derivative for b, what do you get? 4x minus 1. And when you take the derivative for c, what do you get?
4x minus 1.
Okay, so we came up with one option, but all three of these actually have the derivative of 4x minus 1. So based on that information, what I want you guys to do is I want you to come up with a function that could represent all possible antiderivatives of this. Okay, so what did you guys write for f of x? F of x equals what? We know it's this part. 2x squared minus x, and then what? Plus c, exactly. So there has to be that constant value, that just number, and we will use c as our constant that we're going to be working with. So now what I'm going to have you guys do is continuing to build on this. Now we're going to look at finding the antiderivatives of x to the n. So now what I want you to do is I want you to be able to work backwards with x to the n, where n is an integer. That's element of z. So that's going to be that integer value that you're looking at. So go ahead and complete the table below. What I've already done is I already did the antiderivative of x. So the antiderivative of x is 1/2 x squared plus c. So go ahead and figure out what you think those antiderivatives would be. Again, you can always test it by taking the derivative of it to see if you get what you started with. So if it was x squared, it's going to be now x to what power? The third plus c, but then what do I have to do to this? Multiply by 1/3 or divide by 3. Good. If it's x to the third, now this is going to be x to the 4th divided by 4 plus c. And then if it's x to the 4th, that becomes x to the 5th divided by plus c. Good. Which means if we have a power, x to the n, and we're going to have multiple different things along the way. It's not just going to be those basic ones. But if we have a function, its antiderivative is going to be given by the following situation. So if we have x to the n, it becomes x to the n plus 1. So we add 1 degree to it, and then we have to divide it or multiply it by the reciprocal of that new power plus c, provided n doesn't equal -1. So this is always your rule for finding antiderivatives for powers. So therefore, go ahead, do A. So x to the 9th over 9. Make sure you use capital F of x. And then don't forget your constant of integration plus c. I have a feeling many of you are going to lose that constant of integration. It happens every year. Always beware, whenever you take the antiderivative, always go back and put that plus c, because again, as our first example showed, we had 3 different derivatives that were all the same. So we had to bring in that constant. So now when we do this one, this is a power. It just goes to the -3rd power. So therefore, f of x, capital F of x, is equivalent to, so add 1. This gives me x to the -2nd divided by -2 plus c. And of course, we wouldn't leave a negative exponent. So we would write that as capital F of x equals 1 over -2x² plus c. Take a moment, try to do c by yourself. Feel free to write it as a fraction. This is why you guys had to do that pre-stuff. So that's x to the 3/5 power. So when I anti-differentiate that, subtract 1 from the degree. Add 1 to the degree, which gives me 8/5, which means I'm going to divide by 8/5, which is the same thing as multiplying by 5/8 plus c. So what we're doing is we're just trying to find the function. We're trying to find the antiderivative of the function. So we're finding what our new function is. We'll be using that new function for other pieces as well as we continue to move through, but right now we're just practicing that. Now we have what's called an indefinite integration. So we have this integral sign. So this here means we're going to take the antiderivative of it. So this integral means we're taking the antiderivative. So just like if I give you this, d dx of a function, 2x² plus 3, that means find the derivative. This notation means find the antiderivative. Okay, so that's what the notation is going to tell you. So based on that are some other notation feats. So this is all in here, so it's called the indefinite integral. We'll find definite integrals as well. It's the antiderivative of f with respect to x, or the integral of f with respect to x. This x has to match whatever this letter is. So these will always match up. Otherwise, we won't be able to integrate, or we'll have to do some kind of crazy substitution. And don't forget that constant of integration. Again, this part here, this function is called the integrand. Just some vocabulary for you. So here are some integration rules. 3 basic rules, or these basic rules, have a corresponding integration rule. So we had a power rule for derivatives. We have a constant multiplier for derivatives. We have sums and differences, and we have a constant. So these are all of our different rules that we learned with derivatives. They also have integration rules on the right-hand side. So if I'm taking the derivative of a power, that power comes down, we subtract it. Now when we integrate, we go vice versa. We make our power bigger, and we divide by it. If I have a constant that's times my function, when I take the derivative, I can pull that constant out and then take the derivative of that function. Same thing works with integration. If I have a constant times a function, pull that constant out, integrate, and then multiply by that k value. If I'm looking at sums or differences, when I do derivatives, I take the derivative of each individual function. When I integrate, I can integrate each individual function. Okay, sums and differences. There is no product or quotient here. No products or quotients. And then if I take the derivative of a constant, it's always 0. Where if I anti-differentiate a constant, it's always going to be x to the 1st times that k value. So just a couple of different pieces here. Some special cases. If I'm integrating 1 over x, remember, if I'm integrating the natural log of x, if I'm taking the derivative, excuse me, let me state that again. If I take the derivative of the natural log of x, it's 1 over x. So if I integrate 1 over x, it's the natural log of x. But what you'll notice is there's this absolute value bar here. You need to make sure you don't lose that absolute value bar. IB will do this to you. It's absolute value because you can't take the natural log of a negative number. Okay, so that's why it's the absolute value of x, because sometimes we might have a negative x value, but in order to do the problem, we will have to take the absolute value of it. You'll see some problems in our work. You'll see where it comes up. And then if I integrate e to the x, it's just e to the x, but don't forget the plus c. Don't forget the plus c for either of these two, or in essence, any of them. So let's do some examples of integration. I'm going to give you a couple moments here to see what you can go through with these problems. Again, this is just telling you to integrate. Okay, so integrate x to the 7th. We just did a whole bunch of those problems. So that one's straightforward. This one's a constant. Here's a function, an addition piece, and some not so nice ones. So go ahead. Okay, so when we integrate x to the 7th, that just becomes x to the 8th over 8 plus c. When we integrate 6 with respect to u, that's telling me what variable I'm using. So the variable you have to have in that is a u. So when I integrate that, that's going to be 6u plus c. So that's where that constant of integration, or the with respect to variable, comes into play. Here, so this is going to be 2x to the 4th over 4, which then just plus c. Simplifies to x to the 4th over 2 plus c. Integrating sums, I just integrate each individual piece. So that becomes 4t to the 4th over 4 plus 6t cubed over 3 plus 3t plus c, which simplifies to t to the 4th plus 2t cubed plus 3t plus c. And then the last one gives me x cubed over 3 plus x, oops, fix that, plus x to the 3/2 multiplied by the reciprocal plus c. Okay, and here we have a couple of different ones. So we're integrating 3 over x with respect to x, and then we're integrating e to the x over 5 with respect to x. So take a moment and think about what those would be. Feel free to write down what your thoughts are. For each of these, they have that number in the front. You'll get used to them as they go through, but you can always, again, pull that 3 out. So this is the same thing as 3 integrating 1 over x with respect to x. If it confuses you with that 3 up top, because it's just a constant, we can always pull our constant out of our integrand. So therefore, it's 3. Derivative of 1 over x is the natural log of x. It's the natural log of the absolute value of x plus c. And then for b, again, the same thing. I can factor out, pull out, it's not really factoring, pull out that 1/5, and it's the integral of e to the x dx. And when I anti-differentiate e to the x, that is just e to the x plus c. So I just have that 1/5 times it. Okay, then I didn't put example 4 in your packet. Here's example 4. So I'm going to start with the first one. For the first one, keep in mind, if I was going to find the derivative of this, I'd have to do the power and then chain on the derivative of the inside. So how do we undo a chain when it's this in depth? And the long answer is we don't. What we need to do instead is we need to rewrite this. We need to simplify. So sorry, that's an integration symbol. We are going to have to integrate the product of 2x squared plus 3 times 2x squared plus 3. So I need to expand that whole thing before I can integrate. So therefore, we're going to integrate 4x to the 4th plus 12x squared plus 9 with respect to x. So notation, put parentheses around it because we're taking the antiderivative of that whole thing. So when I do that, I get 4x to the 5th over 5 plus 12x to the 3rd over 3 plus 9x plus c, which is just 4/5 x to the 5th plus 4x cubed plus 9x plus c. For b, because there's just one thing in the denominator, divide the whole numerator by x. When you do that, you are going to integrate 4x plus 2 plus 3x to the negative first with respect to x. Here, let me rewrite that. I'm going to do 1 over x for that one. 3 over x, excuse me. So when we integrate this, we get 4x squared over 2 plus 2x, and integrating 3 over x plus 3, natural log, absolute value x plus c, which then just simplifies to 2x squared plus 2x plus 3, natural log, absolute value of x plus c. A quick reason why I didn't, again, leave it as negative first, because some of you are going to do that, which is perfectly fine because we do that so often. But what you'll notice is if we tried to keep that as a negative x, when I anti-differentiate this piece here, this becomes 3x to the 0 divided by 0, which is undefined. We can't divide by 0. Okay, so that's part of where we get this natural log of x in there. And then c, let me just rewrite it down here. So c was integrating the natural log of e to the 4t dt. So take a moment, think through what you could do. So what is the natural log of e to the 4t? 4t. Because this is an exponent on my argument, so it comes down in front. And the natural log of e is the same thing as log base e of e. That's why we work with natural logs. So therefore, it's just 4t dt. And so when I integrate that, it's 4t squared over 2 plus c, which is 2t squared plus c. So sometimes when you do these, you have to simplify first before you even try to anti-differentiate. Other times, you can just jump in and just do the antiderivative. So homework to practice these sections, this is all we've got for this lesson, are the following 3.